In the current state of affairs, there are many experts who have been taught that the average response time is some nominal number like 1.0 in some jurisdictions and 1.5 in others. And I've seen reports that say, well, this is a commonly accepted response time or an accepted standard. I've even seen people refer to this as a standard. And that has never been true. That has never been true of anybody that is aware of reaction time research. Because in 1868, when one of the first reaction time studies were done, they invented the hip chronoscope. That's this thing here. This is the world's first stopwatch that measured in milliseconds. And the purpose of this invention was to measure how reaction times changed when you changed the stimulus. When you changed the stimulus, you got a different response and a different response time. In this study, they also tested groups of people, and they'd test a group of people at one task, change the methodology by one factor, and test that group again. I'll give you an example. Suppose I test a group of 100 of us, and everything's the same except I'm testing in daytime. Now I change only one thing. Everything else is exactly the same, but now I test at night. Suppose in the first trial, average response time was 1 second. And in the second trial, average response time was 1.2 seconds. We can then conclude from those two trials that the influence of nighttime changed response time by 0.2 seconds. This is exactly the methodology used by Franz Donders in 1868, and it's the same methodology used today in our research. That we compare the methodology of the studies, we look over at all the studies, and we see how response time has been influenced by intersections versus mid-block path intrusion, by day versus night, by a hazard directly straight ahead versus 15 degrees to the right or left. And we can see how response time has changed, right? And we can see many times how response time has not changed, like due to gender, and other factors that haven't affected response time. Experience has not affected response time. So why not use a nominal number, right? It might be the middle of all the numbers out there. Well, as has been ruled in some of the courts here in the United States, that it's abstract and inappropriate. And why is it abstract and inappropriate? Because it doesn't fit any particular event. Right? So with a nominal response time, we don't know when the study started the response time. Does that change response time? Certainly it does, and I'm going to explain that later. How about ending point? How much of the response time is accounted for? Is that, if you use 1.5 second response time or a 1 second response time, does that include leg movement time? Does that include the time to press the brake down to get 0.4 G or hard braking or more?
So the RAC do an annual survey, of course, and the most recent one has suggested that around 3% of drivers are using a handheld mobile phone on every single journey that they make. And a further 3% are having a hands-free conversation on every single journey that they make. And that's only those that have responded, and those that have responded honestly. So we're talking about a significant proportion of drivers driving distracted. So we've got a reduced number of drivers to kind of mitigate all that activity, which I personally find pretty scary given what I spend my time doing. So let's get to the detail of what happens when you use your mobile phone behind the wheel. Well, many of you will be aware of all of these things. So drivers who use their phone are 4 times more likely to be involved in a collision than a driver who does not use their phone. The thing that got me interested in this area of research was that statistic and the follow-up statistic, which is you're 4 times more likely to be involved in a collision, but that effect persists for around 5 minutes after you've finished using that phone. What that tells us is it's not just about manually touching a phone or looking at a phone. There's something going on in the brain. There's some kind of cognitive distraction. And that's what our research is focused on. So you're 4 times more likely to crash. You are far less likely to notice any hazards. Those hazards that you do notice, you will take significantly longer to react to, which means, you know, longer reaction times and longer stopping distances. Distracted drivers often show very similar pattern of behaviour to drink drivers. So poor lane discipline doesn't necessarily mean swerving all the way out of their lane, although that does happen quite a bit. But, you know, moving around within the lane a bit more than you would expect a driver who's paying full attention. They'll also make variable speed choices, and this tends to match the demands of their phone conversation. So they might slow down while they're having a particularly challenging conversation, or, you know, that conversation needs more attention at that time, and then they might suddenly speed up. And they use compensatory strategies, which is a polite way of saying they don't check their mirrors and they don't use their indicators. And this is a kind of subconscious attempt to reduce the task demands. So the driver wants to maintain that phone conversation. So they kind of reduce the demands of their attention for the driving task. You know, I don't need to look in my mirrors, really. I don't need to indicate. I know where I'm going. The road's quiet. And that allows that driver to maintain those 2 tasks up to a point. And I think I've already pressed this point enough. We don't improve any of these factors by using a hands-free mobile phone. It's all about cognitive distraction. Now, I realise I'm talking to a very informed audience, but I'm also very used to talking to audiences who don't believe me.
So, principles and an overview. What we want is the user location, which we describe as unknown coordinates X, Y, Z of the user. We know where the satellite is. So you need to suspend your disbelief there and trust me that we know where the satellite is. So satellite location X, Y, and Z. And we measure the range from the known location of the satellite to the user receiver. That doesn't tell us where the user is. That describes a sphere around the known location. So everything of the same range describes a sphere around that, which passes through the user location, but doesn't uniquely define it. In order to get the user location, I need a second satellite measurement. So in a 2D sense, 2-dimensional sense, I need a second, and the intercept of the 2 spheres is the user location. And that is a simple piece of maths, which is a solution to the simultaneous equations where the range is the square root of the difference in the square of the coordinates. So dx squared is the user minus the satellite squared, etc. And in a 2-dimensional case, that is simply solved by 2 simultaneous equations. It's a little bit more complicated than that, but that is the nub of how GNSS works. Obviously, it's 3D, not 2D. So we need a third satellite. The other thing that I mentioned was that we're measuring the range to the satellite. We measure the range on the basis that we know the speed of light. So the radio transmission from the satellite is traveling at the speed of light. So if we know the time between signal arrival and signal departure, we know the range. But we can't know the time of arrival unless we position a synchronized atomic clock at the user, which obviously we don't want to do because that's very expensive. So what we actually do is introduce an extra unknown into the equations, which is the offset of the receiver clock from system time. And we now need 4 simultaneous equations for users X, Y, Z, and the clock offset. And this is why in GNSS systems, we intrinsically, when we solve the navigation equations for position, we get time for free. It's a necessary part of how SatNav works, and it can give us enormous benefits in terms of understanding speed of user and so on. Now, in the modern world, there are a lot more measurements available than that. With GPS alone, there will typically be 8 to 10 visible satellites. With other systems, that can double, treble, quadruple even. So the equations then become an overdetermined set of equations. There are the same number of unknowns, but there are a lot more measurements contributing to the solving of those equations. So we can now get some extra information out. We can identify any potentially faulty measurements, as long as there's not too many. And we can do some quality checking. But the satellites are moving. They're going about 8,000 miles an hour. It depends on the system, and it depends how precise you want to be, but for our purposes today, they're going 8,000 miles an hour. So we don't want to describe that as an XYZ. We instead provide that as a Keplerian orbit descriptor that describes the path, and then we look for points along that path as we're doing the calculations. We actually have to do a little bit of relativity in here. So for those of you that thought you were doing measurements on a crash scene, you actually do need to worry about relativity as well. Unfortunately, you don't, because somebody has worried about that in the receivers, and we have to make corrections for the speed of the satellites, and we have to make corrections for the gravitational potential of the satellite height as well. The signals are extremely weak, so the transmit level from a satellite depends on how much power you can have in the satellite, which you can only garner from solar energy. So the satellite looks as though it has wings, which it looks as though it's flying with enormous great wings, but those are solar panels. Their sole purpose is to capture the sun's energy. And that energy is the only thing that the satellite can use to make its transmissions. So the transmissions from GPS satellites are around 50 watts. So these beasties have a radio signal, which is effectively the brightness of a not very bright electric light, and they are 20,000 kilometers away. So as you will imagine, the signal is not very strong when it gets to us, and it's only through the magic of spread spectrum signal processing that we can recover that, because it sits below the radio noise floor and has to be extracted. As well as that complexity, the user will be moving. The signal transmission environment includes disturbances, and it delays the signal so that the signal doesn't universally travel at the speed of light. There are objects which can obstruct the satellite signals and attenuate them. There are objects that can reflect the signal so that the path that we've measured is not quite correct because it's bounced off a building. There is also radio noise, and there is potentially interference in to that radio signal. And all of that environment is also changing. On top of that, the users don't want the XYZ that we just calculated. They never want that. Latitude, longitude, and height is often wanted, or a conversion to the Ordnance Survey grids. But all of that can be done, and it works. So all of that is solved. In summary, the satellites are carrying precisely synchronized atomic space clocks, which have been corrected for relativity. And we accurately know where the satellites are. A receiver takes measurements from multiple satellites and correlates those signals to measure the pseudo ranges. The pseudo range is the name that we ascribe to a range plus the clock offset. And we then solve that for the 4 unknowns of 3-dimensional position and time. And we can also get velocity out of that by measuring the signal Doppler.